Okay, well, hello guys. My name is Brian Broom-Peltz. Thank you, by the way, for all your presentations. They've been extremely interesting, and this has been a great opportunity to check out your guys' program to kind of see what the field looks like. It's always a exciting experience to see how other people are trying to tackle these problems. So, as you kind of got a sense from this morning, I guess you weren't here this. Yeah, you were here this morning, I believe, right? Anyways. We've been using this toolkit called PetaVision. We also developed it at the New Mexico Consortium, and the content of my presentation will kind of motivate the basis for the research, some of the key features of our software, and then I'm just going to walk you through in a pretty simple example of how to implement your own experiment in the software with kind of the underlying motivation for us that we want people to use it, and we're pretty proud of it. So without further ado, I'm going to start off with I assume a pretty simple question. What is the object on the screen? Yeah, it's an apple. It's an orange, yeah, okay. So I think the next question, which might be a little more difficult, is what's the square root of that number? And so identify x. And this sets up, again, those sorts of different types of problems, one being image classification, the other being numerical calculations. One that's quite easy for humans, image classification and numerical calculations are not as obvious to do with great speed, but they set up two types of problems, one that's easy for humans and hard for computers, and vice versa. So I think this poses kind of an interesting line of inquiry is why is it easy for us to identify an apple but hard to do the square root of a large number? And so I think from the neuroscience background perspective is let's just see how this information is passing through the system. So the light is reflected and received on the retina, and there's some pre-processing there, and it passes to the visual cortex. So very quickly we went from just looking at an apple to a very dynamic and integrated system that, as we understand now, is vastly more complex. But we understand likely that it has to do with the structure, the dynamics of these things. So then the task to trying to understand this and the other problem is there a way to try to capture that? So what is the distinction between how we go about trying to understand objects in a scene and how we could essentially simulate that in those dynamics and capture them in a computer system, right? So if we're going to try and simulate the dynamics, let's try and understand that just from maybe a structural perspective. Let's look at a biological neural network and then the analog, which would be artificial neural network. In this case, we have the black dots in this drawing on the left from a mouse neocortex represent the neurons, and then the lines are the dendrites and axons that connect them. As you can see, again, they're organized in these different layers, and let's make the analogy and say, again, these circles will be our neurons and the lines will be the connections. And you guys are all very familiar with this sort of model. So let's look at the most simplistic artificial neural network that you guys are also familiar with is the idea of a perceptron, where we have inputs that are received by a neuron or a processor in this kind of image. And that processor then does some operation and produces an output. So stepping through how a perceptron does its thing, we have we'll set the inputs as 5 and 10, and then the subsequent step is the weights, where you multiply those inputs, and they are then received as a weighted input by the neuron, or the processor in this image, and subsequently you sum those inputs, so we have a value of -6, and then for us, as in terms of a design and feature, you get to say, okay, when given some value, do what? And in this case, let's do the trivial, whatever the sign is of the processor, we'll set that as the value. If it's -1, or if it's negative, it'll be -1, positive, +1. In this case, it's negative, so it's -1. And so I think that the main thing I really want to draw out of this slide is that you can see that if you set the weights to be different, you'll get a different outcome. So if you say you set weight 1 to have positive value, you'll be getting a positive output despite having identical inputs. So this kind of draws the necessary insight that when we talk about what a network has learned, it's stored in the weights. And that's how information is able to pass through this system and be processed in an intelligible and dynamic way. So necessarily, if you're going to train an artificial neural network to do something useful, even if you start off, as you were showing, with random feature maps or and in any of these descriptions that we've been talking about, there has to be some way that you can go about training those weights to have that information be represented. Some different learning strategies that you guys probably know about in supervised, unsupervised, or reinforcement learning. And you can see here, if it does a good job for classifying the apple to say, encourage it, high five. If it does a bad job, then punish the weights proportional to that error. So Perceptron's a pretty trivial example of this sort of calculation, but when we're talking about doing large tasks on full vision, like right now we're surveying the room and we talk about like identifying a motorcycle, but you can do a whole scan of this room, colors and all the depths and all the full complexity of really what's happening. That task becomes astonishingly large. So let's just do the math of what that looks like. And in this case, you have 10 billion neurons, let's say, just in the visual cortex. Okay, and for each one, they have about 10,000 connections. And now let's say for each neuron as a stream of information passes through this system, let's just say that's like 10 flops per neuron. And then if you multiply that all together, you're now at a petaflop of happening per frame of data. That's really big, and to kind of give that into context, let's say this MacBook right here, that comes out to about 370,000 linked MacBook Pros if you're just going at 1 frame per second. So if we're going at the 24 frames per second kind of human video movie kind of thing, that's 8 million or almost 9 million MacBook Pros. That's a lot of computation just to kind of feel what's going on. That's going at top speed and somehow all integrated. This gives us the point that if you're going to try to do these sorts of simulations, you want to have a system that can be scaled, that can be integrated, that can somehow manage to move all this information around in an efficient, worthwhile process. And so a lot of the different strategies that we've been talking about, either at Upside or these different things, either talk about, in as Dan was talking upstairs, about like the algorithm is in the hardware. And so that's something that is clearly, like, as if we're bringing the power down, definitely like a target.
The hardware is the algorithm.
Yeah, I think that's what he said, I believe. Yeah. So as a projection of this stuff, when we're talking about operating computers and doing these sorts of vision tasks, so eventually that's where you're going to want to integrate it if you want to do it at power scales that seem reasonable. But in terms of exploring how to go about that, in terms of your simulation, you're going to want to have something that can really accomplish those tasks, but in a reasonable and scalable environment. So just remember that that petaflop number that brings us to, I guess, the title of the slide, which is PetaVision. PetaVision got its name because it was the first scientific software to operate at the petaflop scale, running on the Roadrunner computers, I think at 1.22 petaflops. And so yeah, that brings us to the content of the presentation. We got to pass the motivation. Sweet. Step 2 is explaining PetaVision. So here's some of the core features of PetaVision. It's open source and developer friendly, and namely that is an object-oriented C++, fast execution in C. We have put a lot of effort focusing on optimizing for parallelization, and I'll speak a little more of that in the next slides, but we got, yeah, I'll speak the next slide. And then a core feature about PetaVision is the idea that the activity, when we talk about these neurons and V1, V2, all this layers, as we describe it, is based on the local connectivity, so that a neuron only needs to know about the neurons that are connected to it, and vice versa, what it is connected to. And then from just a user experience, all the experiments are designed through a text file. So it makes it really easy to, I can just share with you my text file and be like, okay, you can run your own experiment. And then you could load weights and other files like that, and those are things that would be relevant. Yes?
So parallelization, you have CPUs and GPUs up there. Does that also have an interface to like a distributed computing platform like cluster kind of things? Cluster? You just mentioned that. So
Oh, baby.
Oh, baby. I got a slide for that. You just get ready. Yeah. No, it's a very good question, and I will address that in a moment. So here we go. Parallel acceleration. So 3 of the main tools that we take use of for doing these sorts of parallelizations are OpenMP, GPUs, and we prefer NVIDIA because their cuDNN library is excellent, and the OpenMP for starting different processes. So OpenMP allows us to... OpenMPI, correct, sorry. OpenMPI allows us to split an image and move it onto different machines. So that's really good if you have a server cluster, or imagine you're doing this in the cloud or whatnot. And then OpenMP is something that allows you to, in this case, you see in the bottom right of the image, do convolutions from a sparse layer onto the the dense error layer, and then vice versa. If you're going to be doing from a dense layer to a sparse layer, then it makes more sense to be using a GPU. So where it makes sense, we take advantage of the corresponding hardware and algorithms to do that. And if you look at the code, you can kind of follow through, and Shen has been the driving force for increasing our parallelization, and every other week or so, we're like, oh, I got an order of magnitude speed up. So thanks, Shen. So yeah, this is one of those things that, in terms of appreciating what this as an open source software platform can do for you as a computational neuroscience scientist, this is really one of those big scaling things. And this, in conjunction with this slide, because now we're in the age of cloud computing, not just any cloud computing, Amazon cloud computing, this is really where it's possible for you to have like the firepower of a great software package with the gas of like any size computer that you want for pennies per hour. That's what it's when I first realized how much you could do. It's great. So you can right now go on Amazon and get your own PetaVision AMI. We have all the tools that we normally use for analysis with already installed, and you could have a run going in with an hour. So it's pretty. Yeah, so Amazon, it's an Amazon machine image, I believe that's what the acronym stands for. Yeah, exactly. And so you just load it. I'd recommend using one of their large GPU instances, because I think last time I checked it was 25 cents per hour for 32 cores and an NVIDIA card. So.
Four GPUs.
Yeah, so that's
6,000 shader. Yeah, I said physical shader cores, right?
Yeah, so that's cool, and that's available to you right now. And so, in the same idea that with our local clusters, you can either make one instance or link them together with MPI. And so, even if you got those large clusters, you can get 12 of those clusters and compute to the moon, whatever you want. So we've been able to show that you can link them together, and this is, I think this is those two aspects, the fact that it's open source, acceleratable, and also the fact that you have the cloud on demand really means that you can, if you have questions about how to do this stuff, you have the toolkit to play with it and really, to whatever your heart's extent, to try to ask questions. No, just for graphical purposes. In terms of the numbers that you want to use for MPI, a consideration is about dividing the image in such a way. Sure. Yeah. 4 is just typically, it just looks good to do 4.
Well, I thought there was overlap, so diminishing returns take effect pretty quickly.
Yeah. The halos are that's the information that has to be passed between the machines, and that's what allows us to separate the processes.
Well, and there's kind of a bottleneck.
Yeah.
We usually compute that, so usually the halos are really good, but a little bit less so on the cloud. But sure, at some point you have too many MPI instances. He's just saying like the surface to volume just starts to kill you.
Sure.
Yeah, if you're mostly Halo.
It's going to be more passing information than computing it. So if you want to be the person to find that limit, that'd be cool. So it hasn't been an issue yet. And so another really fun feature is that we already have analysis tools for you. You want to see what your weights look like. You want to get a histogram, track the error, the sparsity. All these things are analysis_network.m in the mlab folder. Yeah, we've been there's been some development of Python scripts to do an analysis, but we've taken more initiative in working in Octave in particular. But it's cool. Let's do it. That's the spirit we need. So And then just for a brief overview, again, we started off with an NSF grant in 2008, and now we are being funded by DARPA and with the SALSA program, which and Upside, all those things that brought us out here. So as you've heard today, some of the ways that PetaVision has been used before, from either depth reconstruction, action classification with Wesley and Shen. Earlier, you learned about some whole image classification on the Cypher dataset. And the thing is, you can use PetaVision instead of an SVN for doing classifications. You can just do an SLP from your sparse layer and then just read that out if you prefer to do that. For example, I just remember you talking about that. And then we've even been using for like multimodal datasets or multi-int linked dictionaries. There's a lot of applications, and I like PetaVision, and I want you to like it too. So in order to persuade you about that, I'm going to kind of walk us through one of these standard V1 LCA setups, so you can kind of see how some of the information moves around. I'm not going to go into too depth, and there's tutorials that are being developed for like precisely making it a clear task about how do you jump in and go from starting an Amazon instance to, okay, cool, I'm just going to let it run and find out what happens. So let's look at a standard V1 LCA. As you see here, as the schematic has, an image is passed to a residual error layer, where then it battles it out with the sparse reconstruction of V1. The line with the arrow those are the weights what we're concerned about learning, and then the line above it is the transpose, and then how it returns back to V1. And then the arrow going to the right for the reconstruction that's actually a clone of those weights that were being projected from the V1 onto the error. And so at this point, it's assumed that you have an installation of PetaVision in your computer or cloud. You have a params file that you can work with, and then finally that you have some training set, and we'll just use Cypher as an example, to experiment on. So the point now moving forward is, what is this params file? So the params file is essentially just a list of objects and attributes for starting and designing your run, using the same sort of artificial neural network thinking. The data is organized into layers and connections, and the whole thing sits inside of a column. So now let's look at those pieces individually, with the first one being the hypercall. So the hypercall is the big daddy that holds everything, and as you can see, these are some of the parameters, but basically it's describing the duration of the experiment, the dimensions, some basic I/O, and as you can see kind of here, that whole experiment is kind of fits inside, and it's all sort of relative and proportional, at least in scaling wise, to that. So moving forward, the hyperlayer, again, in the kind of analogies that we have to biological neural networks, that's where the neurons kind of are stored. And the way it's useful to describe a layer is in both X, Y, and then feature direction, or dimensions. So let's just look a little closer at one in particular. So the top left is the image layer here, and as we have different classes of layers, a hyperlayer is the superclass of all of them, and movie is one of those subclasses. So since everything was defined relative to the hypercall, if you set the NX scale, in this case, to 1, the corresponding X and Y pixels for the image are 32, because it's 32 times 1. Then to load an image, when you use PetaVision, you just list a text file, and it points to, in this case, a text file that has a list of images, and that will point you to a particular image. So now if you see NF, if you set NF to, say, 1, it gives you a grayscale image. It's all you have to do to make a grayscale image and load it into PetaVision. Now, alternatively, say you want to change your NF to 3, it will swap out that grayscale image for a color image, and that's all you have to do. That's again one of those little really nice features of being able to have PetaVision run from a text file. Simple attributes like that if you want to be able to identify independent components. Yes?
So it might be cool in the demo if you said, and if you want to change the scale to 0.5,
and shrink it.
Automatically,
sure.
Might be cool to
Show the movability of those things. This was color changes is a much easier animation in Google. I think PowerPoint has more finesse for scaling animations.
You have to tell the next layer how many features to
Um, Yeah, you-
You change the dimensionality of this layer, you can change the dimensionality of it.
It depends. It depends a combination of the weights that you're using and what you're pointing them to. In this case, so like for example, the V1 layer we have is going to have many more features than say error, and you could arbitrarily set that or expand that as you'd like. The only consequence is the size, the weight patch that's pointing back towards it, which would be the transpose of those. And there, unfortunately, PetaVision has these error checks built into when you do your run, so it will remind you that you messed up and go try again, but it'll point you to where it messed up, which is again one of those really useful things of having in a text document rather than having to recompile the code every single time you make a mistake and do your run. So I think that gives you a good enough overview of this stuff. And there's more parameters that are important and expand the finessing of doing a run, but these are some of the core features to kind of give you a feel for what it looks like. And so in terms of the dynamics of the run, we split it up into these three sort of components, the GSIN, V, and A, or activity and kind of membrane potential voltage. And at the GSIN, that is where the different channels are pooling, the buffers for, say, activating and inhibiting connections from previous layers. That is then passed to the membrane potential where you can have some math occurring from the GSIN, and then subsequently you can again pass that to activity, which is then that's the value that is passed out to all the subsequent layers. So it's segment, it's like a little sub-layers inside of the layer that you have running, and it allows you to set these different things like thresholds. You can set your own functions of how the dynamics of that layer. But again, essentially this is what's happening at every neuron in the thing, and it's quite straightforward for setting up those dynamics just by.
So the V there, instead, like for instance, instead of having a summation, you could have a different function that
Sure.
would apply to all some sort of fold over the input.
Mm-hmm. Yeah, and with LCA you can have like lateral competition and stuff, and you can have things interacting with others. But yes, exactly. That's one of the things that you could embed into the description.
Well, you have the subclass, right? I mean, so this is actually a subclass. This is a layer subclass that implements LCA. Again, LCA neuron.
Yeah.
But you could, like, there are other subclasses that implement. You can integrate the fire neuron.
Yeah, no, it's an interesting generalization of Perceptron. You can still build a Perceptron with this. You have all the tools to do it. It's just but you can do more. There's something that I've played with in the past.
Yes.
Actually, this is just an ANA.
Yeah. Right now you're not looking at the competitive effects right now. This is just showing in general what's happening. But the idea being that with this basic toolkit, and you can be aware of where the other things are, you can do those things and any dynamic that you want to experiment with. And so also a lot of the subclasses you can add parameters to scale them. A recent subclass we made was Momentum Con, which it's been really great for learning weights in a much more efficient way. But without getting too off track, that's just to kind of give that kind of as an idea. So now that we've kind of seen what a hyperlayer can be, one of them being the movie layer, it's good to note that, again, as I alluded to, you can have any arbitrary size of features, again, with the kind of up-down being the feature dimension. But now let's focus more on the final element, which is the hypercon. So as you see here, it connects the neurons to other neurons. And that's, again, the point that we really want to have a system that can go about learning this stuff. So in a kind of a trivial one-to-one example, you have the image matching to the corresponding feature layer in the error. And so each of these are mapped at the same XY coordinate in the image. And so I guess also in this case, the error is of the same X, NX, and NY scale. So now if you kind of expand that along the length of the image, we have X1, X2, X3, and X4. Again, those are still all in the same Y slice, but then to kind of help you visualize it, I'm moving them. This is each of those clusters corresponds to a point in the XY space of the 3 features. I'm not sure if this is the best visualization of this idea, but I hope you can kind of see that it's possible to just make one-to-one connections with the corresponding elements. And so those are one-to-one connections, but the connection, again, that I suggested that is the most important for us to learn in terms of doing these sparse reconstructions is the one going from, in this case, the V1 to the error. So this is something where we want to go from a space that has a lot more features to then having something where there's fewer features, as you were asking about. In this case, also, the consideration is the patch size. So in the scale, as you see here for V1, the NX and NY scale is 0.5, and the NX and NY scale for the error is 1. So you'll see that for every kind of cluster of 2 elements, 2 row columns, I guess, in the error layer, there's 1 in the corresponding. On the top is the error. This is the whole error layer. This is the whole V1. And each one of these elements corresponds to a different feature kind of dimension. In V1, correct. And so right now we're looking essentially at to see it as a slice. And so this could be x equals 1, x equals 2, x equals 3, but we're looking at one static slice through y of the same location.
And the scale is what does some kind of, it's a little bit of cooling over neighborhoods, or
well,
sort of.
the scaling is what allows us to implement a stride of the patches over the image that you're involved in. So in this case, say NFP, as you see, is going to be 3. The reason that we have, for this hypercon, it says V1 to error, the reason it's 3 is because that's telling this that from the V1 to the error, you're going to have to, for each one of these, you're going to have to look at 3 elements in the feature dimension. So as you see right here, the illustration, that's precisely what happens. So in this case, we have the NXP, NYP equaling 2, so as it matches to 2 elements. Now, the way that PetaVision is built, you have to do them in corresponding multiples of that minimum. So in this case, the next option would be 4, and that allows us to then see where you can have overlapping patches. And then you can imagine seeing this in a much larger scale, 16, but that would be a really messy diagram. So, but I think the next thing to see is that each one of these kind of sets of arrows, imagine now stepping down and having this point to all the corresponding elements over here, all the neurons. That collection is our basis vector, and that's the thing we're trying to learn. And so I tried to illustrate that by showing how, even though these are different neurons in the X dimension, or X space, the idea is that while we're doing these LCA algorithms, like if this neuron is activated from some amount, that means that the patch that's being projected on the corresponding location matches a common Gabor or some image. And so in this case, we have a feature Gabor, and this is a color opponent kind of cell. And so again, that's one of the cool things that you can also do in PetaVision is have shared weights, and for both computation reasons and also the kind of assumption that the natural scenes are translationally invariant from just the sort of basis vectors that you want to use to represent them.
So
You don't have to have shared weights.
But it's not necessary, but you can.
how do you make the 2 features different? What's different? Why is that one going to learn this Gabor and that one that one
Oh, that's the magic of LCA, if I understand it correctly.
Because that is an independent component of the universe.
That's the
I
idea.
fated to learn that.
Yeah.
It may not be the first feature.
Yeah, I just picked one that happened to look like a Gabor and one that happened to be a color opponent.
At this point, these are just slots where something will be learned.
Yes, that's right.
Exactly.
And
And so
what gets
so
shown there is not deterministic.
Yeah, it seems to be very related to the random initial conditions. Yeah, so genetics is fate. I don't know what
and so as you'll see here, I'll actually step through that. And so that same idea, each of these elements corresponds to a Gabor, weight patch, or dictionary element, whatever variant of phrase you want to use, a feature. And so they start off, we can start them off as random weights. And then as you train your network, they will go from random static noise and to fully formed and beautiful Gabors. So this is something that only took 10 or 2 million time steps, which I think took me 3 hours, not long, to go through. But again, depending on the system that you have and how many cores and GPUs link up, you can scale that time. But I don't know really times corresponding time numbers for you to look at for this.
I think because that's on Cypher, the picture I mean, those are cooler than the ones, right? Because you're learning those on Cypher, and I think because it's so downsampled, there's just a lot of richness. Yeah, those are. You have some good wars in there. You got some ways that look almost like sky, right? Which makes sense, yeah. Like I see a cow.
Do you have a sense of like, is there much support for these things? Like how many images contributing strongly to this? Like,
Yeah.
So I don't know.
For 10,000 images, is that?
It's not really that big. So like you're getting like an image, you would have an explicit version of support, like the parts, the inputs that are contributed to this.
Oh.
And you don't have that in like, you also have it for your learning. Like I was a master map creator for following inputs.
Yeah, so this is a heavy rule.
So I guess in that case, the notion of support would be like how many competitions did you win, and because I found like
We keep asking questions.
yeah. So like when I've done TV stuff, sometimes like I can't tell. Like sometimes things look like total noise junk. Sometimes things will look like just one of my inputs, and then sometimes it will look like sort of like reasonable feature, you know. And when it looks like one of my inputs, the question is always like, did you learn something amazing, or did you just learn to recognize one of my training examples? And
That's always a hard question.
That's absolutely.
so like you can't need to. You just explicitly say what's your support. How many inputs did you win? And if you're only like 2, it's like okay, well it makes sense you look like a cat because you're just a picture of a cat.
So what are these things competing for? They're competing for the ability to recognize something, or I mean, how are
They're
they?
competing for the right to contribute to the reconstruction.
Right, but how does one win? Oh, the reconstruction. That's right.
You win this sparsity.
If you are, then how is the reconstruction done exactly? Can you do that?
You're the maximal output.
I just explicitly set up new slides to go and describe the LCA. I think one thing to realize is that LCA is an algorithm you can use
Okay.
to use PetaVision.
You can also use backprop.
You can use backprop, you can just use XLP, whatever you want, but this is just an example of some ways that you can learn. And also, these images also, again, popped out of that easy to use analysis software. So again, that I'm more speaking on to PetaVision, but those are all things you can ask and explore using the software. So actually, this brings me to the end of the conversation about it. If you want to go check out more information, we have a link, more information about running it on Amazon. There's plenty of details about how to run this simulation software on your own computer, on your own servers. PetaVision.sourceforge.net. If you have any questions about LCA, I think we can talk about them over dinner. That sounds like a really good idea. But it's been a long day. Thank you very much for your time, company, and that's PetaVision.
I want Brian to film this talk.
I just did it.
Oh, really?
Done.
Well, okay. Well, yeah, maybe. So you just got your voice
And the screen capture.
Well, maybe that's good enough.
I'm on it. No, I'll superimpose that. I'll do a green screen and walk in front of the. Yeah. Well, no, I'll edit that. I'll just actually only put my beard. Maybe. Yeah. Yeah, that'd be cool.
Right. The game where where's Brian?
Yeah. I think you'll have
What sort of like
you'll just have a beard bias.
single feature